Exercise number 32 asks us to evaluate this integral given here, a triple iterated integral, by changing to cylindrical coordinates. Looking at the differentials, we see that this is expressed in terms of x, y, and z. So let's begin by figuring out which region in space this integral is being integrated over, what its domain is. And then we can figure out how best to translate this into cylindrical. So we see that x is ranging from -3 to 3. So let me jot that down here. Y runs from 0 up to the square root of 9 minus x squared. And z is bounded between 0 and 9 minus x squared minus y squared. So there's kind of a lot going on here. Let's kind of figure this thing out. So the integral dz is on the inside, with dy and dx on the outside. So let's start by just looking at the xy plane and see what's going on there. So we'll have, I'm trying to figure out where I want to place all of these things. So x is going from -3 to 3, and y is following that. So let's call this 3, -3, 3. X goes from -3 to 3. Y is bounded below by 0, so the x-axis, and it's bounded above by the square root of 9 minus x squared. Hopefully you've done enough things with this by now that you can recognize that this is going to be the top half of a circle with radius 3. If not, of course, write y equals the square root of that square, rearrange. You'll get x squared plus y squared equals 9. So we get, this is of course, as usual, going to be drawn very crudely. That's terrible. But anyway, y goes from 0 up to that curve. So this is the projection or footprint of the region of integration in the xy plane. Within that, we see that z is bounded below by 0 and above by 9 minus x squared minus y squared. So if you would like, you can sketch kind of a quick graph of what that looks like. Not sure how best to position this, but whatever. X is going from -3 to 3, and y we have that so we have that kind of circular arc there. In the z direction, we're starting at 9, and we have this minus x squared minus y squared. That is so a downward opening elliptical, or rather circular paraboloid. So you have this sort of region in the XYZ space here. This part is less important to work out in this particular case because we have these clear bounds on z, and the conversion between rectangular and cylindrical is usually pretty easy as far as z is concerned because they both still have a z-axis. It's x and y that we need to be most concerned with. So actually, let me go ahead and bring that back out. It's a poor drawing anyway, and we don't really need it. Because if we re-express this thing, we see that if we write this in polar, in the xy plane, we have bounds on r from 0 to 3, right? And from the origin, we're always going from 0 up to 3 in whichever direction we go. So our upper bound on r is a constant 3. Theta, we see, runs from 0 to pi. Now for the bounds on z, z mostly stays the same, except we want to change this into polar. X squared minus y squared, negative x squared minus y squared. Of course, you can factor out that negative sign and make that an x squared plus y squared, which means that the upper bound on z is 9 minus r squared. This is very nice and straightforward here. This is frequently the case when working when moving between rectangular and cylindrical. The bounds on z usually don't change much except to alter the algebra into the new space. So you use your usual algebraic conversions and you're fine. The xy constraints are usually what we have to readjust. So if we call this integral I for convenience, we can now say that, so we have all of this stuff here, so we can say that the original integral I is equal to, now rebuilding this in cylindrical. I'm not sure, let's see how much space we'll need here. Let me leave myself plenty of space and we'll see what's going on. We have the square root of x squared plus y squared. Of course, that is r. We also have this dz dy dx. That represents a dv volume element. And when we're translating into polar or cylindrical, we have to remember that there's another factor of r to consider. And now we need dr, d theta, and dz in some order or another. I was trying to do there. Okay. The order is somewhat constrained by the fact that z is in terms of r. So let's go ahead and stick that on the inside to have it as safe as possible. Z goes from 0 to 9 minus r squared. So there is our inner integral. And then the next two moving out, the r and theta, that's a polar rectangle, so we can do those in whichever order we want. Let's just write dr d theta. R goes from 0 to 3, and theta goes from 0 to pi. So we have re-expressed this integral now. We have the integral from 0 to pi, of the integral from 0 to 3, of the integral from 0 to 9 minus r squared, of r times r dz dr d theta. You see how most of these pieces, the outer two integrals had to be fundamentally re-expressed in terms of polar. We had to figure out what domain this was and rewrite that in terms of polar. The innermost integral, this stuff dz, mostly stayed unchanged. We just adapted the x and y to be in terms of r and theta, in this case just r. We have to remember the insertion of this scaling factor of r to make the areas work out right, or volume in this case. And then the integrand itself, square root of x squared plus y squared, that nicely simplifies down to r. So that's very nice. If this were more, if this was something else, you could have a messier integrand here. You could use your x equals r cosine theta, y equals r sine theta, and simplify as necessary. But here is an expression of that integral. And we are asked to evaluate it. So let's begin working on that. Looking through here, let's see if there's anything we can separate out. The integral dz depends on r in its bounds, so we can't pull that out of the dr. But we notice that nothing else depends on theta. So we can separate out the integral from 0 to pi d theta. And then we have times the integral from 0 to 3 of the integral from 0 to 9 minus r squared. R times r is r squared. dz dr. So now let's do one more step of evaluation here. The integral from 0 to pi d theta will be pi. That's the length of that interval. You could, of course, integrate that and get your theta and blah, blah, blah. Now we have times the integral from 0 to 3 of this inner integral. We have this integral r squared dz. So r squared is constant with respect to z. So we have r squared z evaluated from z equals 0 up to z equals 9 minus r squared. There's our upper bound there. dr. And you see now at this point, this is written as a mostly finished, z equals 0 will just be 0. We'll have an r squared times a 9 minus r squared. Then you just have a calc 1 style integral evaluating, integrating a polynomial. We have a pi out front. We'll get another constant here. We'll leave that to you to confirm for yourself that after all of these simplifications, we get 162 fifths times pi. Unless you're certain that you can't use the practice, you should finish that up and make sure you get that result. On the other hand, if you are certain you don't need the practice, and those sorts of integrals are no problem for you, then probably fine there. But that's the idea here. When we ask questions on exams, we have a tendency to try to separate setting up from evaluating. You are likely to see questions that ask you to set up but not evaluate certain integrals, and other questions where you're asked to evaluate integrals. So a problem like this would usually be more in terms of, write this in cylindrical. Because, of course, if you make an error, then everything else after that is going to be all kinds of bad. But I'm not writing the final, so I don't know exactly what's going to be on there. Just be aware that there are a variety of different questions that we could ask about this. But I felt this was a good example because it illustrates several things, looking at a given triple integral, reconstructing the shape of its domain, translating that, expressing that in terms of cylindrical coordinates, and then using that region, which could have just been given to us, right? They could have just told us, oh, we have, this could have just been described as we want to integrate over the region that is above z equals 0, the xy plane, below z equals 9 minus x squared minus y squared, that paraboloid. So we could take the region below the paraboloid, above the xy plane, and when y is non-negative. So, that we could solve and find the intersection here. Y being non-negative would give us just this side. So they could have described this mostly in words with just a couple equations. And we could reconstruct the same region that way, and then just set up our integral directly in cylindrical. I keep wanting to say in polar because, cylindrical is really just polar with a z-axis pasted on. So most of the, if you've been doing okay with the polar integrals and also with the triple integrals in rectangular, this shouldn't be too bad. It's really just combining those two ideas.